Alright, what I want to look at here is the period of a binary system. What I want to show is that when you've got two bodies, we'll call this one 4m1 and we'll call this one m1. When you've got two bodies rotating about each other, you should know already that they rotate about the center of mass, which I'll put just there. But what I want to just show here is that the period for the rotation is the same for both of them. Might seem trivial and obvious, but let's just show that it is so. So center of mass is there. I know that you all can do the center of mass calculation. That's the one where you do the x equals m1 x1 plus m2 x2 all over m1 plus m2. If you do that, you'll find that the center of mass here, and we'll call this distance out to this one r1, and we'll call this distance r2. You'll find that r1 is 1/4 of r2, or 4 r1s equal r2. 4 r1s equal r2. Now, there's a centripetal force acting to make each of those masses go around this center of mass. And the centripetal force, as I'm sure you're well aware, comes from the gravitational force between the two bodies. So let's write down what that gravitational force is. It's F equals big G m1 times 4, because that one's 4 times bigger than that one, all divided by the distance between them squared, which is r1 plus r2 all squared. Now, we don't have to worry about that stuff. That's all going to work out, so we don't have to expand those brackets or anything like that. And we could have just substituted in the r2 equals 4r1, and we would have had 5r1 squared or 25r1 squared, right? So now we've got the force between them, and that force is supplying the centripetal force to keep those guys going in a circle. Let's write down those little equations. So v1 is going to be the velocity of the left-hand body, and v2 the velocity of the right-hand body. So we can say v1 squared over r1 times the mass, which is 4m1, must be equal to that equation, big G m1 4 over r1 plus r2 squared. We can do the same for the right-hand side body, which is just v2 squared times m1 all over r2 in this case. Again, it's from the center of mass, is equal to that same m1 4 all over r1 plus r2 squared. Now we can do a little bit of simplification here. We can get rid of those m1s on the left hand one. We can get rid of the m1 on this one. We've still got the same equation on both sides, so we can actually say that 4v1 squared over r1 is equal to v2 squared over r2. Now, if we have a look at the v1 and v2, and we can write that as v1 is equal to 2 pi r1 all over t1. You could say v2 is equal to 2 pi r2 all over t2. At this stage we're saying the t1 period for body on the left and t2 the period for the body on the right to rotate about that center of mass. We're saying they might be different, so we'll call them t1 and t2, but hopefully we'll see that they're the same. So now if we resubstitute that stuff in there, resubstitute in v1 here, we've got 2 pi, we'll square it immediately, so we'll say it's 4 pi squared r1 squared all over t1 squared all times 4, so that would come out at 16, and we've got the divided by the r1, and we can say that's equal to the v2 squared, which is 4 pi squared r2 squared all over t2 squared, and all divided by the r2. Now we can simplify this guy down. We've got 4 pi squared on both sides, that can go. We got rid of the r2 on that one, that one's gone, the r1 on that one's gone. So what are we left with? We're left with 4 r1 all over t1 squared is equal to r2 over T2 squared. But we've said that 4R1 equals R2, so we can get rid of that and make that an R2. Now we've said R2 equals R2 all over T1 squared over T2 squared. So what we've basically said is that T1 squared must equal T2 squared. So we've proved that the period for those bodies to rotate about each other is the same. And we're done.